Hey, welcome to our peaceful corner of the universe. I'm so happy you're here with me today. There's something truly magical about taking a moment to step away from the rush of everyday life and diving into the extraordinary mysteries that surround us. Whether you're curled up in your favorite chair, taking a quiet walk, or simply looking for a moment of wonder, you've come to exactly the right place. I know the world can feel overwhelming sometimes with all its noise and constant demands for our attention. But here, in this endless space we're creating together, we can slow down and explore the most fascinating questions that have captivated humanity for generations. We're going to embark on a journey that will take us to the very edges of space and time, where the familiar rules of our everyday world bend and twist in the most beautiful and mind-bending ways. So take a deep breath, let your shoulders relax, and allow yourself to be curious. Today we're going to discover something truly remarkable together, and I promise to guide you through it with the same gentle care you'd want from a trusted friend sharing their favourite story by a warm fireplace. Today we are diving into the fascinating world of what happens to time near a black hole. It's one of those questions that sounds like pure science fiction, yet it's grounded in some of the most elegant and proven theories in all of physics. We're going to explore how these cosmic giants, these mysterious regions of space, where gravity becomes so intense that not even light can escape, actually bend and stretch time itself in ways that would seem impossible if we hadn't discovered them to be beautifully, remarkably true. As we journey together through this cosmic mystery, you'll discover how a simple thought experiment about falling elevators led to revelations that changed our understanding of reality itself. We'll explore gentle analogies and vivid imagery that will help you visualize concepts that even seasoned physicists find awe-inspiring. And most importantly, we'll do it all at a pace that feels comfortable and natural, building understanding step by step, like a friendly conversation that unfolds over a perfect afternoon. Imagine, if you will, that you're sitting by a peaceful lake on a perfect summer evening. The water is completely still, like a mirror reflecting the first stars beginning to appear in the darkening sky. You pick up a small stone and gently toss it into the water. What happens? Beautiful ripples spread outward in perfect circles, moving at a steady pace across the surface. The ripples are regular, predictable, and they move through the water at a speed that seems natural and constant. For most of human history, we thought time was just like those ripples, steady, predictable, and flowing at the same rate for everyone and everything in the universe. We imagined time as a great cosmic river, carrying us all along at exactly the same speed, like passengers on a vast invisible boat. Whether you were sitting in your garden, climbing a mountain, or even if you could somehow travel to the most distant star, time would tick by at exactly the same rate. A second would always be a second, an hour would always be an hour, and if you had a perfectly synchronized watch with someone on the other side of the galaxy, they would always show exactly the same time. This intuitive understanding of time made perfect sense to us. After all, it matched everything we experienced in our daily lives. The clock on your wall ticks at the same steady rate, whether you're reading a book, running up the stairs, or lying perfectly still. The sun rises and sets with reassuring regularity. The seasons cycle through their ancient dance with a rhythm that our ancestors could count on for thousands of years. Time felt like the one constant, the unchanging backdrop against which all the drama of life played out. But here's where our story begins to take a fascinating turn. Like a mystery novel, where you discover that the most obvious answer is far from the whole truth. Deep in the hearts of physicists and astronomers, questions began to emerge that would ultimately revolutionize our understanding of time itself. They noticed peculiar things about light, strange behaviors in the cosmos that didn't quite fit with the simple, steady river model of time. Consider the light from distant stars. Light travels incredibly fast. So fast that it could circle our entire Earth more than 7 times in just 1 second. Yet when we observe stars, we're not seeing them as they are right now. We're seeing them as they were when the light left them, sometimes years, sometimes millions of years ago. The light from our own sun travelling at this incredible speed still takes about 8 minutes to reach us. This means that if the sun suddenly disappeared, we wouldn't know it for 8 whole minutes. We'd still see it shining in the sky, still feel its warmth, completely unaware that it was already gone. This realization opened up profound questions. If light takes time to travel, and if we're always seeing the past when we look at distant objects, what does this mean for our understanding of now? Is there really a universal now that applies everywhere in the universe simultaneously? Or is the very concept of simultaneity, of things happening at the same time, more complicated than we ever imagined? These questions might seem abstract, like philosophical puzzles that don't affect our daily lives, but they would soon lead to discoveries that would reveal time to be far stranger, far more flexible, and far more beautiful than anyone had dared to imagine. The steady river of time, it turns out, is more like a flowing stream that can speed up or slow down, that can be stretched like taffy or compressed like a spring, depending on where you are and how fast you're moving. And nowhere is this strange behaviour of time more dramatic, more extreme, or more mind-bending than in the vicinity of black holes. Those cosmic monsters where gravity becomes so intense that it literally warps the fabric of space and time itself. But to understand how we discovered this incredible truth, we need to meet one of the most brilliant minds in human history, a man whose gentle curiosity and thought experiments would unveil secrets of the universe that still take our breath away today. Picture a young man working in a patent office in Switzerland at the beginning of the 20th century. His name was Albert Einstein, and while his day job involved examining other people's inventions, his mind was constantly wandering to the deepest questions about the nature of reality. He had wild, unruly hair that seemed to reflect the wild, unruly ideas brewing in his brilliant mind, and unlike many of his contemporaries who relied on complex mathematics and elaborate experiments, Einstein had a gift for what he called thought experiments. Simple, elegant scenarios that he could imagine in his mind to test the fundamental laws of physics. One of his most famous thought experiments was beautifully simple. Imagine you're in an elevator, he said, but this isn't an ordinary elevator in an ordinary building. This elevator is floating in the vast emptiness of space, far from any planets or stars. Suddenly, the elevator begins to accelerate upward at a steady rate. As it accelerates, you feel pressed against the floor, just as you would if you were standing on the surface of a planet with gravity. Now here's Einstein's brilliant insight. If you're inside that elevator with no windows, no way to see outside, there would be absolutely no experiment you could perform to tell whether you're accelerating through space or simply standing still in a gravitational field. The feeling of being pressed against the floor would be identical in both cases. Drop a ball, and it would fall to the floor at exactly the same rate whether you're being pulled down by gravity or pushed up by the elevator's acceleration. This might seem like a simple observation, but it was revolutionary. Einstein realized that acceleration and gravity are not just similar. They are fundamentally the same phenomenon viewed from different perspectives. This insight, which he called the equivalence principle, was like finding a key that unlocked an entirely new understanding of the universe. But Einstein's curiosity didn't stop there. He began to wonder what this equivalence between gravity and acceleration meant for light itself. Imagine that elevator again, but this time picture a beam of light shining across it from one side to the other. If the elevator is accelerating upward, then by the time the light beam reaches the other side, the elevator will have moved slightly upward. From your perspective inside the elevator, it would appear that the light beam curved downward, following a slightly bent path rather than a perfectly straight line. Now, remember the equivalence principle. If acceleration and gravity are the same thing, then light must behave the same way in a gravitational field as it does in an accelerating elevator. This led Einstein to a stunning conclusion. Gravity bends light. Not because light has mass in the traditional sense, but because gravity itself isn't really a force pulling on objects. Instead, gravity is a curvature in the very fabric of space and time. To help visualize this revolutionary idea, imagine a large stretched rubber sheet, the kind you might use as a trampoline. If you place a heavy bowling ball in the center of the sheet, it creates a deep depression, a curved region where the sheet bends downward. Now, if you roll a marble across the sheet, it won't travel in a straight line. Instead, it will follow the curves created by the bowling ball's weight, spiraling around the depression, or even falling into it if it's moving slowly enough. Einstein proposed that this is exactly what happens in space, except instead of a rubber sheet, we have the fabric of space-time itself, a mysterious invisible medium that permeates all of reality. Massive objects like stars and planets create curves and depressions in this fabric, just like the bowling ball on the rubber sheet. And just as the marble follows the curves in the sheet, objects moving through space follow the curves in space-time. What we experience as gravity isn't really a force at all, it's simply the natural tendency of objects to follow the straightest possible path through curved space-time. This insight explains so many mysteries that had puzzled scientists for generations. Why does the Earth orbit the Sun? Not because the Sun is somehow reaching out and pulling on the Earth, but because the Sun's enormous mass creates such a significant curve in space-time that the Earth's natural straight-line motion becomes a graceful orbit around that curve. Why do we feel gravity on Earth's surface? Because we're constantly trying to follow our natural path through space-time, but the Earth's solid surface prevents us from doing so, creating the sensation of weight. But perhaps the most mind-bending implication of Einstein's theory was what it meant for time itself. If space and time are woven together into a unified fabric called space-time, and if gravity curves this fabric, then gravity must affect not just the paths objects take through space, but also the rate at which time flows. In regions where space-time is more curved, where gravity is stronger, time itself must slow down relative to regions where space-time is flatter. This wasn't just a theoretical curiosity. Einstein's equations made specific, testable predictions about how time would behave in different gravitational environments. Near massive objects, where gravity is strong, time would tick more slowly compared to regions far from massive objects where gravity is weak. The difference might be tiny in most everyday situations, but it would be measurable, real, and absolutely fundamental to how the universe works. And this brings us to one of the most important realizations in the history of science. Time is not the steady, unchanging river we once imagined. Time is flexible, malleable, and intimately connected to the structure of space itself. It can be stretched and compressed, sped up and slowed down depending on the gravitational environment in which it's measured. This discovery would ultimately lead us to understand how time behaves in the most extreme gravitational environments in the universe. Near black holes, where gravity becomes so intense that time itself undergoes the most dramatic transformations imaginable. Let's take a moment to really understand what Einstein discovered about gravity, because it's so different from our everyday experience that it can seem almost magical. Imagine you're a child again, lying on your back in a field of soft grass on a warm summer day, looking up at the clouds drifting lazily across the blue sky. From your perspective, lying there on the ground, it feels like the earth is solid and stable beneath you, and the clouds are moving through empty space above. But Einstein's revelation tells us that what's really happening is far more beautiful and strange. The Earth, with its enormous mass, is actually creating a kind of invisible valley in the fabric of space-time itself. You can't see this valley, you can't touch it, but it's as real as the ground beneath you. And you're not lying still at all, you're actually in constant motion, falling through this curved space-time following the most natural path possible through the geometry of the universe. The only reason you don't feel like you're falling is that the solid surface of the Earth is constantly pushing back against your natural motion through space-time. It's like being in a car that's accelerating forward. You feel pressed against the seat not because there's a force pulling you backward, but because the seat is preventing you from continuing in your natural state of motion. Similarly, gravity isn't pulling you down toward the Earth. Rather, the Earth's surface is pushing up against your natural tendency to follow the curved path of space-time. This insight helps us understand why astronauts in orbit around the Earth experience weightlessness. They're not beyond the reach of Earth's gravity. In fact, they're well within it. But they're freely following their natural path through the curved space-time around Earth, with nothing to push against them and create the sensation of weight. They're in a constant state of freefall along with their spacecraft, following the same curved trajectory through space-time. It's only when something like a rocket engine or the surface of a planet interrupts this natural motion that we experience the sensation we call weight. Now, here's where things get truly fascinating when we start thinking about time. Remember that space and time aren't separate things, so they're woven together into a single unified fabric called space-time. When gravity curves space, it must also curve time. And just as objects follow curved paths through the spatial dimensions, the flow of time itself follows curves through the temporal dimension. To help visualize this, imagine time as a river flowing through a landscape. In flat, open country, the river flows straight and smooth at a steady pace. But when the landscape becomes hilly and mountainous, the river must follow the contours of the land. It might slow down as it flows uphill, speed up as it rushes downhill, or even pool in valleys where the terrain creates natural basins. Gravity affects time in a similar way. In regions where space-time is relatively flat, far from massive objects, time flows at what we might call its natural rate. But as we approach massive objects, where space-time becomes increasingly curved, time begins to slow down relative to distant regions. The stronger the gravitational field, the more pronounced this effect becomes. This time dilation effect has been measured and confirmed in countless experiments since Einstein first predicted it. Atomic clocks, which are among the most precise timekeeping devices ever created, run measurably slower when placed in stronger gravitational fields. A clock at sea level, where Earth's gravity is slightly stronger, will tick more slowly than an identical clock on a mountaintop, where gravity is slightly weaker. The difference is tiny, just a few nanoseconds over the course of a day, but it's real, measurable, and absolutely crucial for technologies like GPS satellites to work properly. GPS satellites orbit high above the Earth, where gravity is weaker than it is on the surface. This means that time flows slightly faster for the satellites than it does for us on the ground. If we didn't account for this gravitational time dilation, GPS coordinates would drift by several kilometers every single day. The fact that your phone can pinpoint your location to within a few meters is actually proof that Einstein's theory of gravity is correct, and that time really does flow differently in different gravitational environments. But even more fascinating than these small everyday effects is what happens when we consider truly massive objects. Objects so massive that they create extreme curvatures in space-time. Stars, for instance, are so massive that they create significant gravitational time dilation. Time flows more slowly on the surface of our Sun than it does here on Earth. On the surface of a neutron star, the collapsed core of a massive star where matter is compressed to unimaginable densities, time flows so slowly compared to our reference frame that what seems like hours to an observer on the neutron star would appear as days to us watching from a safe distance. These extreme examples help us begin to appreciate what happens near the most massive, most gravitationally intense objects in the universe, black holes. But to understand black holes and their effect on time, we need to first understand how they form and what makes them so special. The story of black holes is really the story of stars, how they live, how they die, and what happens when gravity wins the ultimate cosmic battle against all other forces in the universe. As we prepare to explore these cosmic monsters, keep in mind that everything we've learned about gravity and time applies even more dramatically in their vicinity. If a simple star can slow down time, and if a neutron star can create even more extreme time dilation, imagine what happens when we approach an object where gravity becomes so strong that space and time themselves become almost unrecognizably distorted. That's the realm we're about to enter together, where the familiar rules of physics are pushed to their absolute limits and beyond. To understand black holes and their incredible effects on time, we need to begin with stars, those magnificent, blazing furnaces that light up the darkness of space. Imagine a star not unlike our own sun, but much, much larger. This giant star has been burning for millions of years, its core a raging inferno where nuclear fusion constantly converts hydrogen into helium, releasing tremendous amounts of energy that keep the star shining and create an outward pressure that balances against the inward pull of the star's own gravity. For most of a massive star's life, this is a beautiful, stable dance. The nuclear fire in the core pushes outward with exactly the right force to balance gravity's inward pull. The star maintains its size and shape, burning steadily and peacefully, just as our sun has done for billions of years and will continue to do for billions more. It's like a cosmic balloon, where the outward pressure of the hot gas inside perfectly balances the inward squeeze of the balloon's material. But unlike our sun, which will eventually fade quietly into a white dwarf star, massive stars face a very different fate. As they burn through their nuclear fuel, they begin to create heavier and heavier elements in their cores. First hydrogen becomes helium, then helium fuses to create carbon and oxygen, then these fuse to create neon, magnesium, silicon, and eventually iron. Each step in this process releases less energy than the step before it, like a fire that gradually consumes all the easily burned material and begins to struggle with what's left. When a massive star finally creates iron in its core, something dramatic happens. Iron is special, it's the most stable element in the universe. Unlike lighter elements, iron cannot be fused to release energy. In fact, fusing iron actually requires energy rather than releasing it. So when a star's core becomes mostly iron, the nuclear furnace that has been burning for millions of years suddenly shuts down. It's like a fire that runs out of oxygen. The energy source that has been fighting against gravity for the star's entire life simply stops. What happens next occurs in a matter of seconds, but it's one of the most spectacular and violent events in the universe. Without the outward pressure from nuclear fusion, gravity wins decisively. The star's core, which might have been the size of Earth, collapses to a point just a few kilometers across in less than a second. The collapse is so rapid and so complete that it's almost beyond human comprehension. Imagine the entire Earth compressed into a ball the size of a city, then compressed even further. The outer layers of the star, suddenly finding nothing to support them, crash down toward the collapsed core at speeds of up to 30,000 kilometers per second. When this infalling material hits the incredibly dense core, it bounces back outward in a colossal explosion called a supernova. For a brief time, this single star can outshine an entire galaxy containing billions of other stars. The explosion is so violent that it can be seen from billions of light years away, and it scatters heavy elements throughout space, seeding future generations of stars and planets. But our focus today is on what happens to that collapsed core. If the original star was massive enough, more than about 20 or 25 times the mass of our Sun, then even the incredible forces unleashed in the supernova explosion cannot stop the core's collapse. Gravity is simply too strong. The core continues to collapse beyond the point where it becomes a neutron star, beyond the point where matter as we know it can exist, beyond the point where even the basic structure of atoms can survive. The core collapses into what physicists call a singularity, a point of theoretically infinite density where the normal laws of physics break down. Around this singularity, gravity becomes so intense that it creates a region of space from which nothing, not even light itself, can escape. This region is called the event horizon, and the entire object, the singularity plus the event horizon, is what we call a black hole. The event horizon is not a physical surface like the surface of a planet. It's more like an invisible boundary in space, a point of no return. Anything that crosses the event horizon, whether it's matter, energy, or even information, is doomed to fall toward the singularity at the center. From the outside, we can never see what happens beyond the event horizon. It's as if that part of the universe becomes forever hidden from us, sealed off by the extreme curvature of space-time itself. The size of the event horizon depends on the mass of the black hole. A black hole with the mass of our Sun would have an event horizon only about 3 kilometers in radius, so small that you could walk around it in about 20 minutes if it was somehow safe to do so. But stellar mass black holes typically have masses many times that of the Sun, making their event horizons correspondingly larger. The supermassive black holes found at the centers of galaxies can have event horizons larger than our entire solar system. Now, here's where our understanding of gravity and time becomes crucial. Remember that gravity curves space-time, and that this curvature affects the flow of time. Near a black hole where gravity is incredibly strong, space-time becomes so severely curved that time itself behaves in ways that seem almost impossible to believe. As we approach a black hole, time begins to slow down dramatically compared to the rest of the universe. And at the event horizon itself, from the perspective of a distant observer, time appears to stop completely. This is not science fiction or theoretical speculation. It's a direct consequence of Einstein's theory of general relativity, and it's been confirmed by observations of real black holes throughout the universe. The first direct image of a black hole's event horizon was captured in 2010, showing the supermassive black hole at the center of the galaxy MP7. This image, showing the glowing ring of matter swirling around the black hole's event horizon, provided visual confirmation of many predictions about how black holes should appear and behave. As we prepare to explore what it would actually feel like to approach a black hole, and what would happen to time during such a journey, remember that these are real objects with real, measurable effects on space and time. They're not just mathematical curiosities or science fiction concepts. They're among the most extreme and fascinating objects in the universe, places where the very fabric of reality is stretched to its absolute limits. Now comes the most mind-bending part of our journey together. Let's imagine, in the most gentle and carefully controlled way possible, what it would be like to approach a black hole and experience firsthand how time behaves in such an extreme gravitational environment. We'll create a safe, comfortable thought experiment where we can explore these ideas without any of the very real dangers that would make such a journey impossible in reality. Picture yourself as an astronaut in a specially designed spacecraft, approaching a large black hole from a safe distance. You have a trusted friend staying behind in a spacecraft far from the black hole, in a region where space-time is relatively flat and time flows at what we might call a normal rate. Both of you have identical, perfectly synchronized atomic clocks, and you have a reliable communication system that allows you to exchange messages. As you begin your approach toward the black hole, something beautiful and strange starts to happen. At first, when you're still far away, everything seems normal. Your clock ticks at its usual rate, your friend's messages arrive at regular intervals, and the black hole appears as a dark sphere against the starry background, surrounded by the brilliant glow of superheated matter spiraling into it. But as you get closer, you begin to notice something remarkable. The messages from your friend who is staying safely far away start to arrive more and more frequently. It's as if your friend is speaking faster and faster, or as if time in the distant region is speeding up compared to your own experience. But from your perspective inside your spacecraft, nothing has changed. Your clock is ticking at exactly the same rate it always has. Your heartbeat, your breathing, your thoughts, everything feels completely normal. What's happening is that time is beginning to slow down for you relative to your friend in the distant spacecraft. As you move deeper into the black hole's gravitational field, where space-time is increasingly curved, your personal time begins to stretch out compared to time in the flatter regions of space. Your friend, watching from a distance, would see your clock ticking more and more slowly as you approach the black hole. But you, experiencing time from within your own reference frame, notice no change in your own rate of time. Instead, you perceive the distant universe as speeding up around you. This effect becomes more and more pronounced as you get closer to the event horizon. When you're at a distance of perhaps 100 kilometers from the event horizon, time is flowing noticeably slower for you than for your distant friend. Messages from your friend are arriving so frequently that they seem to blur together, like a recording played at high speed. If you could look back toward the distant universe, you might see stars evolving through their entire life cycles in what seems like mere hours from your perspective. As you continue your approach, getting closer and closer to the event horizon, this time dilation effect becomes more and more extreme. At 10 kilometers from the event horizon, time is flowing much more slowly. At 1 kilometer away, the effect is dramatic. At 100 meters away, time dilation becomes so severe that seconds in your reference frame correspond to hours or even days in the distant universe. And here's where the story takes on an almost poetic quality. As you approach the event horizon itself, time dilation approaches infinity. From the perspective of your friend watching from a safe distance, it would appear that your approach toward the event horizon slows down more and more until you seem to freeze in place, hovering just outside the event horizon like a photograph suspended in space. Your friend would see the light from your spacecraft becoming redder and redder, dimmer and dimmer, until it fades away completely. To your friend, it would appear that you never actually crossed the event horizon. You seem to remain forever frozen at its boundary, but from your own perspective, something very different happens. You continue to experience time at what feels like a perfectly normal rate. Your clock keeps ticking steadily, your thoughts flow naturally, and you don't feel like you're slowing down at all. From your point of view, you cross the event horizon in a finite amount of your own time, perhaps just a few seconds or minutes after you began your final approach. This is one of the most beautiful paradoxes in physics. Two different observers can have completely different yet equally valid experiences of the same event. Your friend never sees you cross the event horizon, while you experience crossing it in a completely normal way. Both perspectives are correct within their own reference frames. There's no contradiction here. It's simply a manifestation of the relative nature of time itself. Once you've crossed the event horizon, you've entered a region of space-time that is completely cut off from the external universe. No information about what happens inside can ever reach your friend on the outside. From the perspective of the outside universe, you have effectively disappeared, frozen forever at the moment of crossing. But from your own perspective, you continue to exist and experience time, even though you're now inevitably falling toward the singularity at the center of the black hole. Inside the event horizon, space and time themselves become strangely twisted. The direction toward the singularity becomes as inevitable as the forward flow of time in normal space. Just as you cannot travel backward in time in normal circumstances, once inside the event horizon, you cannot avoid moving toward the singularity. It's not a matter of having enough rocket fuel or thrust. The very geometry of space-time inside the event horizon makes escape impossible. This thought experiment reveals something profound about the nature of time and reality. Time is not the universal steady flow we once imagined. It's intimately connected to gravity, to the curvature of space-time, and to the observer's position within that curved geometry. Near black holes, where gravity reaches its most extreme values, time behaves in ways that challenge our everyday intuitions, but reveal the deeper, more beautiful truths about how the universe really works. As we conclude this first part of our gentle journey into the mysteries of black holes and time, take a moment to appreciate how far we've come together. We've discovered that time itself is not fixed but flexible, that gravity is not a force but a curvature of space-time, and that black holes are real, observable objects that push these effects to their most extreme limits. In our next part, we'll explore even more fascinating aspects of how black holes interact with time, space, and the fundamental nature of reality itself. To truly understand what happens at time near a black hole, we need to gently pull back the curtain on one of the most beautiful and profound discoveries in all of science. Picture, if you will, the universe not as empty space dotted with stars and planets, but as something far more extraordinary. Imagine space and time woven together like the most delicate silk, creating a fabric that stretches across the entire cosmos. This fabric, which scientists call space-time, is not just the stage upon which the cosmic drama unfolds, it is an active participant in every moment of existence. When Albert Einstein first proposed this revolutionary idea in the early 1900s, he fundamentally changed how we think about reality itself. Before Einstein, we imagined space as a fixed, unchanging container, like a vast empty box that held all the stars and galaxies. Time, meanwhile, was thought to tick away steadily, like a cosmic metronome that kept the same beat everywhere in the universe. But Einstein's gentle genius revealed something far more enchanting. Space and time are not separate entities at all, but rather two aspects of a single unified reality that can stretch, compress, and even curve. Think of it this way. Imagine you're lying on a soft, stretchy trampoline on a peaceful summer evening. The trampoline represents the fabric of space-time, perfectly flat and smooth when nothing disturbs it. Now, if you place a heavy bowling ball in the center of that trampoline, something magical happens. The fabric dips and curves around the ball, creating a gentle depression that extends outward in all directions. This is precisely what massive objects like stars, planets, and especially black holes do to the fabric of space-time. They create curves and valleys in the very structure of reality. But here's where the story becomes even more wondrous. If you were to roll a marble across this curved trampoline, it wouldn't travel in a straight line. Instead, it would follow the curves created by the bowling ball, spiraling around it in graceful loops. This is exactly how gravity works in our universe. What we experience as the gravitational pull of the Earth isn't really a force pulling us downward. It's actually us following the natural curves that our planet creates in space-time. We're like that marble, moving along the gentlest path through the curved landscape of reality itself. Einstein's insight was so profound that it took years for even the most brilliant minds of his time to fully grasp its implications. He showed us that massive objects don't just sit passively in space, they actively reshape the very fabric of existence around them. A star doesn't just occupy a position in the cosmos, it creates a dimple in space-time that extends far beyond its visible surface. A planet doesn't merely orbit that star, it follows the curved pathways carved into the structure of reality by the star's immense mass. As we float through this cosmic story, it's important to understand that space-time isn't just a metaphor, it's as real and tangible as the ground beneath your feet. When you drop a pebble into a still pond, you can see the ripples spreading outward in perfect circles. Similarly, when massive objects move through space-time, they create ripples in the fabric itself. These gravitational waves, as they're called, travel at the speed of light across the universe, carrying with them the whispers of cosmic events from billions of years ago. In recent years, scientists have built incredibly sensitive instruments that can detect these whispers from the deep cosmos. When two black holes spiral into each other in a dance that lasts millions of years before culminating in a final cataclysmic merger, they send ripples through space-time that eventually reach Earth. These waves are so subtle that they stretch and compress our entire planet by distances smaller than the width of a proton, yet our instruments can detect them, allowing us to literally hear the universe singing its ancient songs. The more massive an object, the deeper the curve it creates in space-time. Our Sun, massive as it is compared to Earth, creates a gentle depression that keeps all the planets in our solar system following their orbital paths. But imagine an object so massive, so dense, that it creates not just a depression, but a deep, steep-sided well in the fabric of space-time. This is where our story begins to approach the realm of black holes, those cosmic phenomena that curve space-time so severely that they create what we might think of as bottomless pits in the very structure of reality. Now, here's where the magic of Einstein's discovery becomes most apparent in our daily lives, even though we rarely think about it. The relationship between space and time means that when space is curved by gravity, time itself is affected. This isn't just theoretical, it's something we can observe and measure. If you could somehow hover above the Earth in a spaceship and look down at someone standing on the surface, you would see their clock running slightly slower than yours. The difference is tiny, just a few billionths of a second per day, but it's real and measurable. This phenomenon, called gravitational time dilation, happens because gravity curves space-time, and when space-time is curved, the flow of time is altered. The stronger the gravitational field, the more pronounced this effect becomes. Near the surface of the Earth, the effect is negligible for most purposes, but as we venture closer to more massive objects, time dilation becomes increasingly dramatic. Near the surface of the Sun, time runs about 2 parts per million slower than it does here on Earth. Near a white dwarf star, time might run noticeably slower. But near a black hole, time dilation becomes so extreme that it fundamentally changes the nature of existence itself. To understand this better, imagine time as a river flowing through the landscape of space-time. In regions where space-time is relatively flat, far from massive objects, this river flows smoothly and steadily. But as the river approaches the curved regions created by massive objects, it begins to slow down like water flowing uphill. The steeper the curve in space-time, the more the river of time slows to a gentle crawl. Near a black hole, this river of time moves so slowly that from the outside it appears almost to stop entirely. The story of how we came to understand these cosmic truths is as beautiful as the discoveries themselves. In 1905, a young patent clerk in Switzerland named Albert Einstein was thinking deeply about the nature of light and motion. He wasn't working in a prestigious university or surrounded by the latest scientific equipment. Instead, he was sitting in his modest office, examining patent applications during the day and pondering the mysteries of the universe in his spare time. His gentle curiosity and willingness to question everything led him to insights that would forever change our understanding of reality. Einstein's first breakthrough came when he realized that the speed of light is constant for all observers, regardless of how fast they're moving. This might seem like a simple observation, but its implications are profound and beautiful. Imagine you're standing on the side of a highway watching cars pass by. If a car is traveling at 60 miles per hour and turns on its headlights, the light from those headlights still travels at exactly the same speed, whether the car is moving toward you or away from you. This is fundamentally different from how we normally think about speeds adding together. If you throw a ball forward while riding on a train, someone watching from the platform would see the ball moving at the speed of your throw plus the speed of the train. But light doesn't behave this way. No matter how fast you're moving when you shine a flashlight, the light always travels at exactly the same speed, approximately 186,282 miles per second, or about 300 million meters per second. This speed, which scientists call c, is one of the fundamental constants of our universe, as unchanging and reliable as the rising of the sun. Einstein realized that if the speed of light is always constant, then something else must be flexible to accommodate this constancy. That something else turned out to be time and space themselves. When you move very fast, approaching the speed of light, time literally slows down for you relative to someone who is stationary. This isn't just a theoretical curiosity. It's a fundamental property of our universe that has been confirmed by countless experiments and observations. Consider the story of cosmic ray muons, tiny particles that are created when high-energy cosmic rays from deep space collide with molecules in Earth's upper atmosphere. These muons are unstable and normally decay within about 2 millionths of a second. Given their short lifespan, they should disappear long before they can travel the roughly 10 miles from the upper atmosphere to the Earth's surface. Yet we detect them routinely at ground level. How is this possible? The answer lies in Einstein's discovery about time dilation. These muons are travelling at speeds very close to the speed of light, and at such speeds, time passes much more slowly for them than it does for us. From our perspective on Earth, the muons live much longer than they should, because their internal clocks are running in slow motion. This beautiful phenomenon allows these cosmic messengers to complete their journey from the edge of space to our detectors on the ground, bringing with them information about the high-energy processes occurring in the depths of the cosmos. Einstein's second great insight, published in 1915 as his general theory of relativity, revealed the deep connection between gravity and the curvature of space-time. He realized that what we experience as gravity is actually the result of mass and energy warping the fabric of space and time around them. This was a radical departure from Newton's view of gravity as a force that somehow reaches across empty space to pull objects toward each other. In Einstein's beautiful picture, there is no mysterious force reaching across the void. Instead, massive objects like stars and planets create curves in space-time, and other objects simply follow the straightest possible paths through this curved landscape. When you drop an apple, it doesn't fall because Earth is pulling it down. It falls because it is following the natural contours of curved space-time, taking the path of least resistance through the warped fabric of reality. One of the most elegant confirmations of Einstein's theory came during a solar eclipse in 1919. Einstein had predicted that the sun's mass would bend space-time enough to deflect the path of light from distant stars. During the eclipse, when the sun's bright light was blocked by the moon, astronomers could photograph stars that appeared near the sun's edge. They found that these stars appeared to be in slightly different positions than they would be if the sun weren't there, exactly as Einstein had predicted. The sun's gravity was bending the light from these distant stars, proving that space-time itself was curved. This bending of light by gravity, called gravitational lensing, has become one of our most powerful tools for exploring the cosmos. Massive galaxies and galaxy clusters act like cosmic magnifying glasses, bending and focusing light from even more distant objects behind them. This allows us to see galaxies and quasars that would otherwise be too faint to detect, like looking through a natural telescope made of warped space-time itself. As we continue our gentle journey through these cosmic revelations, it's worth pausing to appreciate the profound beauty of Einstein's insights. He showed us that the universe is far more interconnected and dynamic than we had ever imagined. Space and time are not separate, static entities, but aspects of a single, flexible reality that responds to the presence of matter and energy. Mass tells space-time how to curve, and curved space-time tells matter how to move in an eternal dance of cosmic choreography. The implications of this discovery extend far beyond the realm of abstract physics. Every GPS satellite orbiting our planet must account for the effects of both special and general relativity to maintain accurate positioning. The satellites experience time dilation due to their high orbital speeds, and that they also experience the effects of Earth's gravitational field on the flow of time. Without corrections for these relativistic effects, GPS systems would accumulate errors of several miles per day, making them useless for navigation. Einstein's theories also open the door to understanding some of the most exotic objects in our universe. If space-time can be curved by mass and energy, what happens when you have an object so massive and dense that it curves space-time to its breaking point? This question leads us directly to black holes, those enigmatic cosmic phenomena where Einstein's equations predict that space-time becomes so severely warped that it folds in on itself, creating regions from which not even light can escape. As we settle deeper into our cosmic story, let's explore one of the most beautiful and counterintuitive aspects of Einstein's universe: the relationship between gravity and time. In our everyday experience, we don't notice that time passes differently depending on where we are or how fast we're moving. A second feels like a second whether we're sitting in a chair or running down the street, whether we're at sea level or on top of a mountain. But Einstein's gentle revelations showed us that this perception, while perfectly reasonable for our daily lives, masks a deeper truth about the nature of reality itself. Time, it turns out, is not the steady, unchanging metronome we once believed it to be. Instead, it's more like a symphony where the tempo can vary depending on the circumstances. The conductor of this temporal orchestra is gravity itself, with stronger gravitational fields causing time to flow more slowly, and weaker fields allowing it to flow more quickly. This isn't just a theoretical curiosity. It's a fundamental property of our universe that affects everything from the innermost workings of atoms to the grand-scale evolution of galaxies. To understand how gravity affects time, imagine yourself standing at the bottom of a deep well on a quiet morning. Your friend is standing at the top of the well, looking down at you. If you both have identical clocks and start them at exactly the same moment, something remarkable happens. Your clock, down in the stronger gravitational field at the bottom of the well, will run slightly slower than your friend's clock at the top. The difference is incredibly small, so small that you would never notice it in your daily life, but it's real and measurable with sensitive instruments. This phenomenon occurs because gravity is not just a force that pulls objects together. It's a curvature in the fabric of space-time itself. When space-time is curved by the presence of mass, both space and time are affected. The stronger the gravitational field, the more severely space-time is curved, and the more dramatically time is slowed down. It's as if gravity reaches into the very mechanism of time itself, gently pressing on the gears of the cosmic clockwork. The mathematics behind this effect are elegant in their simplicity. The amount of time dilation depends on what physicists call the gravitational potential, essentially how deep you are in the gravitational well created by a massive object. The deeper you go, the slower time moves relative to observers in weaker gravitational fields. Near the surface of the Earth, the effect is tiny. A clock at sea level runs about 1 part in 10 billion, slower than a clock at the top of Mount Everest. But as we venture to more extreme environments, this effect becomes increasingly pronounced. Consider what happens on the surface of the Sun, our nearest star. The Sun's mass is about 3,000 times greater than Earth's, and its gravitational field is correspondingly stronger. If you could somehow survive on the Sun's surface and look back at Earth through a magical telescope, you would see that clocks on Earth appear to be running about 2 parts per million faster than your clock. This might not sound like much, but over the course of a year, the difference would amount to about a minute, quite noticeable if you were trying to keep appointments. The effect becomes even more dramatic when we consider white dwarf stars. The dense remnants left behind when stars like our Sun reach the end of their lives. A white dwarf typically contains about as much mass as the Sun packed into a sphere about the size of Earth. This incredible density creates a gravitational field so strong that time on the surface of a white dwarf runs about 1 part in 1,000, slower than it does here on Earth. If you could spend a year on the surface of a white dwarf and then return to Earth, you would find that more than a year had passed here while you were gone. But even white dwarfs pale in comparison to neutron stars, those incredibly dense stellar remnants that pack more mass than the Sun into a sphere only about 12 miles across. The gravitational field of a neutron star is so intense that time dilation becomes a major factor in any calculations involving these objects. Near the surface of a neutron star, time runs noticeably slower than it does in the relatively weak gravitational field of our solar system. An observer watching from a safe distance would see events on the neutron star's surface unfolding in slow motion, like a cosmic movie played at half speed. These extreme examples help us understand what makes black holes so extraordinary. A black hole represents the ultimate extreme of gravitational time dilation, a place where the curvature of space-time becomes so severe that time, from the perspective of a distant observer, appears to slow to a crawl and eventually stop altogether. But we're getting ahead of ourselves in our gentle journey. To truly appreciate what happens near a black hole, we need to first understand how these cosmic phenomena form and what makes them so unique. The beauty of gravitational time dilation lies not just in its exotic applications, but in its fundamental role in shaping the universe around us. Every star, every planet, every grain of cosmic dust contributes to the complex tapestry of space-time curvature that permeates the cosmos. The universe is not a static stage upon which cosmic events unfold, but rather a dynamic, ever-changing landscape where the very flow of time varies from place to place, depending on the distribution of matter and energy. This variability in the flow of time has profound implications for our understanding of cosmic evolution. In regions of space where matter is densely packed, such as the centers of galaxies or the cores of massive stars, time flows more slowly than in the relatively empty voids between galaxies. This means that the evolution of the universe proceeds at different rates in different locations, creating a complex temporal landscape that mirrors the distribution of matter throughout the cosmos. When we look out at distant galaxies through our telescopes, we're not just seeing across space, we're also seeing across time. The light from these galaxies has travelled for billions of years to reach us, carrying with it information about how the universe looked when it was much younger. But the story is even more complex than this simple light's travel time would suggest. The gravitational fields of intervening galaxies, dark matter halos, and other massive structures can subtly alter the flow of time along the light's journey, creating tiny but measurable effects that astronomers must account for when interpreting their observations. As we prepare to delve deeper into the realm of black holes, it's worth reflecting on the elegant interconnectedness of Einstein's universe. The same principles that govern the gentle time dilation we experience between sea level and mountaintops also apply to the most extreme environments in the cosmos. The difference is only one of degree. Near a black hole, these effects become so extreme that they fundamentally alter our understanding of what it means for time to flow. To understand what happens to time near a black hole, we must first understand how these extraordinary objects come into existence. The story of black hole formation is one of the most dramatic tales in all of astronomy, involving the death throes of massive stars and the fundamental limits of matter itself. It's a story that begins with the peaceful nuclear fires burning in the hearts of stars and ends with the creation of objects so dense and massive that they tear holes in the very fabric of space-time. Picture a star much more massive than our Sun, perhaps 20, 30, or even 50 times more massive. For most of its life, this stellar giant exists in a state of perfect balance. In its core, nuclear fusion reactions convert hydrogen into helium, releasing tremendous amounts of energy that create an outward pressure. This pressure pushes against the star's own gravity, which is constantly trying to collapse the star inward. For millions of years, these two forces remain in equilibrium, creating a stable, long-lived star that shines steadily in the cosmic night. But this balance cannot last forever. Unlike our Sun, which has enough hydrogen fuel to burn for about 10 billion years, massive stars live fast and die young. They burn through their nuclear fuel at a prodigious rate, consuming in just a few million years what would sustain a smaller star for billions of years. It's like comparing a candle that burns gently for hours to a firework that blazes brilliantly for mere seconds before exhausting itself. As the massive star ages, it begins to run out of hydrogen in its core. When this happens, the delicate balance that has maintained the star's stability for so long begins to shift. With less nuclear fuel available, the outward pressure from fusion reactions starts to weaken. Gravity, patient and relentless, begins to gain the upper hand. The star's core starts to contract under its own immense weight, and as it contracts, it heats up, eventually becoming hot enough to fuse helium into heavier elements like carbon and oxygen. This process continues in a series of stages, with the star's core becoming ever smaller, denser and hotter as it exhausts each type of nuclear fuel. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each stage burns faster than the last, like a cosmic hourglass running out of sand. The hydrogen burning stage might last millions of years, the helium burning stage perhaps hundreds of thousands of years, and the final silicon burning stage just a few days. Iron represents the end of the road for nuclear fusion in stars. Unlike lighter elements, iron cannot be fused into heavier elements in a way that releases energy. Instead, any attempt to fuse iron actually requires energy input, making it useless as a stellar fuel. When the star's core finally consists primarily of iron, the nuclear fires that have sustained it for so long simply stop. The star has reached the end of its ability to generate the outward pressure needed to resist its own gravity. What happens next unfolds with breathtaking speed. Without the outward pressure from nuclear fusion, gravity suddenly becomes the dominant force. The iron core, containing perhaps 1.5 times the mass of our Sun but compressed into a sphere only about 12 miles across, can no longer support its own weight. In less than a second, faster than you can blink your eyes, the core collapses catastrophically. The collapse is so violent and rapid that it defies easy description. The core's density increases by a factor of 100 billion in the space of milliseconds. Electrons are crushed into protons, forming neutrons and releasing vast numbers of neutrinos. The core becomes so dense that a teaspoon of its material would weigh as much as Mount Everest. This is the birth of a neutron star, one of the densest objects in the known universe. But the story doesn't end there. The collapsing core rebounds when it reaches nuclear density, creating a powerful shockwave that propagates outward through the star. This shockwave, combined with the enormous energy released by the neutrinos, tears the star apart in a spectacular explosion called a supernova. For a few weeks, this single exploding star can outshine an entire galaxy containing billions of stars, visible from across the universe as a beacon of cosmic catastrophe. However, if the original star was massive enough, more than about 25 times the mass of the Sun, not even the tremendous forces of nuclear density can halt the collapse. The neutron star that forms in the core is so massive that its own gravity overwhelms even the incredibly strong nuclear forces that hold neutrons together. Nothing in the known universe can stop the collapse now. The core continues to shrink, becoming smaller and denser with each passing moment. As the core shrinks, its gravitational field becomes stronger and stronger. The escape velocity, the speed needed for anything to break free from the gravitational pull, increases rapidly. When the core shrinks to about the size of a large city, the escape velocity reaches the speed of light. At this point, even light itself cannot escape from the gravitational field. The object has become a black hole, a region of space-time so severely curved that it represents a one-way journey into the unknown. The boundary around a black hole where the escape velocity equals the speed of light is called the event horizon. This invisible spherical surface marks the point of no return. Anything that crosses the event horizon, whether it's a particle of light, a spacecraft, or even information itself, can never escape back to the outside universe. The event horizon is not a physical surface like the surface of a planet or star, but rather a mathematical boundary in space-time that represents the limit of causality itself. The size of the event horizon depends on the mass of the black hole. For a black hole with the same mass as our Sun, the event horizon would have a radius of about 2 miles. A black hole with 10 times the mass of the Sun would have an event horizon with a radius of about 20 miles. This relationship, that the event horizon radius is proportional to the black hole's mass, is one of the fundamental properties that makes black holes so unique among cosmic objects. But stellar collapse is not the only way black holes can form. In the early universe, shortly after the Big Bang, conditions were so extreme that black holes could form directly from the collapse of very dense regions of matter and energy. These primordial black holes could have a wide range of masses, from less than that of a mountain to millions of times the mass of the Sun. While we have not yet directly observed primordial black holes, they remain an active area of theoretical research and observational searches. At the other extreme, we have supermassive black holes that contain millions or billions of times the mass of the Sun. These cosmic giants reside at the centers of most large galaxies, including our own Milky Way. The formation of supermassive black holes is still not fully understood, but it likely involves the gradual accumulation of mass over billions of years, either through the accretion of surrounding matter or through mergers with other black holes. Each type of black hole, stellar mass, primordial, and supermassive, creates its own unique effects on the flow of time. The strength of gravitational time dilation depends on how close you can get to the black hole's center while still remaining outside the event horizon. For a stellar mass black hole, you can get very close to the center while still remaining outside the event horizon, leading to extreme time dilation effects. For a supermassive black hole, the event horizon is much larger, so the time dilation effects at the horizon are less extreme, though still significant. As we prepare to explore what actually happens when someone approaches a black hole, it's worth contemplating the profound implications of their existence. Black holes represent the ultimate victory of gravity over all other forces in nature. They are places where the normal rules of physics as we understand them break down, where space and time become so distorted that our usual concepts of cause and effect no longer apply. They are, in a very real sense, holes in the fabric of reality itself, windows into realms of physics that we are only beginning to understand. Now we come to perhaps the most mysterious and profound boundary in all of the universe, the event horizon. Picture, if you will, an invisible sphere surrounding our black hole, marking a border that exists not in space but in the very fabric of reality itself. This boundary is so fundamental, so absolute, that once crossed it changes the very meaning of existence itself. The event horizon gets its name from a beautifully simple yet haunting concept, It represents the boundary beyond which events cannot affect an outside observer. Imagine standing on the shore of a vast, dark ocean at twilight. You can see waves approaching the beach, watch seabirds diving for fish, observe the gentle dance of light on water. But now imagine a line drawn across that ocean, beyond which nothing, no light, no sound, no information of any kind can ever reach you again. That invisible line is what an event horizon represents in the cosmos around a black hole. For our stellar mass black hole, this boundary sits approximately 3 kilometers from the center for every solar mass the black hole contains. So if our black hole weighs 10 times as much as our Sun, its event horizon would be a sphere about 30 kilometers across, roughly the size of a large city, yet containing the compressed matter of 10 entire stars. The precision of this relationship speaks to the elegant mathematics that govern these cosmic monsters. What makes the event horizon so special isn't just that it traps light, it's that it represents a fundamental asymmetry in the universe itself. From our perspective, watching from a safe distance, we would see something extraordinary happen to anyone unfortunate enough to fall toward this boundary. As they approach the event horizon, their clocks would appear to slow down more and more dramatically. Their movements would become languid, dreamlike, as if they were moving through cosmic honey. Picture watching a dear friend falling toward the black hole. As they draw closer to that invisible boundary, you would see their descent slow to an almost imperceptible crawl. The light from their body would shift redder and redder, stretched by the immense gravitational field until it faded beyond the ability of any instrument to detect. To you, it would appear as though they freeze at the event horizon, their image growing dimmer and redder until it vanishes entirely into the darkness. But here's where the story becomes truly extraordinary, and perhaps a little unsettling. From your friend's perspective, falling toward the black hole, nothing special happens when they cross the event horizon. Their watch continues to tick at its normal rate. They feel time passing normally. They don't experience any dramatic moment of crossing a boundary. In fact, for a sufficiently large black hole, they might not even realize they've crossed the point of no return until they're already well inside. This asymmetry in experience reveals something profound about the nature of reality itself. Time, which we experience as universal and absolute in our daily lives, reveals itself to be deeply personal and relative when a gravity becomes extreme. Your friend experiences their final moments unfolding normally, while you experience them as stretched across eternity. Both experiences are equally real, equally valid descriptions of what happens near a black hole. The mathematics behind this seeming paradox flows from Einstein's realization that space and time are woven together into a single fabric. Near the event horizon, this fabric becomes so warped, so twisted by the black hole's immense gravity, that the normal relationships between cause and effect, between past and future, become fundamentally altered. What we think of as now for someone near the event horizon has no meaning for us watching from far away. As we contemplate these ideas, it's worth pausing to appreciate just how far beyond everyday experience we've travelled. In our normal world, if you and I synchronize our watches and then separate, we can call each other later and confirm that the same amount of time has passed for both of us. Near a black hole, this simple assumption breaks down completely. The very concept of simultaneity, of events happening at the same time, loses its meaning when gravity becomes this extreme. As we continue our gentle exploration of what happens near a black hole, we must turn our attention to another fascinating and somewhat sobering aspect of these cosmic giants, the tidal forces that stretch and squeeze anything that ventures too close. These forces tell a story of gravity's increasing intimacy with matter, revealing how the black hole's influence becomes more personal, more invasive, the closer we approach. To understand tidal forces, let's first think about something familiar and comforting: the tides in Earth's oceans. Twice each day our planet's waters rise and fall in response to the moon's gravitational pull. This happens because the moon pulls more strongly on the side of Earth closest to it than on the side farthest away. This difference in gravitational strength across Earth's diameter creates the gentle rise and fall of our tides, a rhythm that has guided life on our planet for billions of years. Near a black hole, this same principle operates, but with terrifying intensity. The black hole's gravity is so strong and falls off so rapidly with distance that different parts of an object experience dramatically different gravitational pulls. Imagine for a moment that you're falling feet first toward our black hole. The gravitational force on your feet being closer to the black hole would be significantly stronger than the force on your head, just a few feet farther away. This difference in force would begin to stretch you vertically, pulling your feet toward the black hole more strongly than your head. At the same time, because all parts of your body are being pulled toward the same central point, you would be squeezed horizontally, as if the black hole were trying to mold you into a long, thin needle pointing toward its center. This stretching and squeezing effect is what physicists call spaghettification, a term that captures both the process and its inevitable outcome with darkly appropriate humor. The distance at which these tidal forces become dangerous depends on the size of the black hole, and this reveals another of the universe's beautiful ironies. For a stellar mass black hole, one formed from the collapse of a massive star, the tidal forces become lethal while you're still quite far from the event horizon, perhaps thousands of kilometers away. You would be torn apart long before crossing the point of no return, your atoms scattered into the cosmic wind. But for a supermassive black hole, one of those wattleage giants at the centers of galaxies that weigh millions or billions of times more than our sun, the story unfolds quite differently. The event horizon of such a black hole is so far from its center that the tidal forces there are relatively mild. You could cross the event horizon of a supermassive black hole and survive, at least initially, experiencing the passage as little more than a gentle pull toward the center. This difference between stellar mass and supermassive black holes speaks to a fundamental principle in physics, the square-cube law. As objects grow larger, their volume increases much faster than their surface area. For black holes, this means that as they grow more massive, their event horizons grow more rapidly than their tidal effects at those horizons. The largest black holes in the universe are, paradoxically, the gentlest to approach. Let's imagine, with a mixture of scientific curiosity and careful caution, what it might feel like to experience these tidal forces gradually. As you fall toward a stellar mass black hole, you would first notice a strange sensation in your body, a feeling as if someone were gently pulling on your feet while holding your shoulders. This wouldn't be painful at first, merely odd, like stretching after waking up from a long sleep. But as you continue to fall, this gentle stretching would intensify. Your body would begin to elongate, your limbs feeling as though they were being pulled by invisible cables. The sensation would be unlike anything possible on Earth, where gravity's pull is essentially uniform across the small scale of human bodies. Here, near the black hole, you would feel gravity's variation across your body directly, intimately. At the same time, you would feel pressure on your sides, as if the space around you were contracting, trying to squeeze you into a narrower shape. Your rib cage would feel compressed, your arms pressed against your body by forces that have no earthly analogue. These aren't mechanical forces, like being squeezed in a vice, but gravitational forces, the very geometry of space itself reshaping around you. The mathematics describing these tidal forces flows from the same equations that describe the gentle rise and fall of Earth's oceans, but scaled up to cosmic proportions. The force difference across your body would be proportional to your height divided by the cube of your distance from the black hole. This cubic relationship means that tidal forces intensify rapidly as you approach. What starts as a gentle tug becomes an irresistible pull, then a destructive force beyond imagination. But let's not dwell too long on the destructive aspects of tidal forces. They also reveal something beautiful about the nature of gravity itself. These forces arise not from any malevolent intent of the black hole, but simply from gravity's desire to treat every particle of matter with perfect equality. Each atom in your body feels the exact gravitational force appropriate to its distance from the black hole. It's only because your body extends across space that these perfectly fair forces create the tidal effect. In a sense, tidal forces represent gravity's ultimate expression of fairness, every particle treated exactly according to its position, with no favoritism, no exceptions. The fact that this perfect fairness can be lethal to extended objects like human bodies speaks to our own limitations, not to any flaw in gravity's character. We are creatures of a gentler gravitational environment, adapted to the mild, uniform pull of Earth's gravity well. Deep within the mathematics that describe black holes lies a number that represents something both simple and profound, the Schwarzschild radius. Named after Karl Schwarzschild, the German physicist and astronomer who derived the solution to Einstein's field equations that describes the spacetime around a black hole, this measurement represents the distance from the center where the event horizon forms. Schwarzschild's story itself is rather poignant and adds a human dimension to our cosmic exploration. He developed his solution to Einstein's equations while serving as a soldier on the Russian front during World War I. Within months of completing this groundbreaking work that would help us understand some of the most extreme objects in the universe, he died of an autoimmune disease contracted during the war. He never lived to see how his mathematical insights would revolutionize our understanding of gravity and time. The Schwarzschild radius has an elegant simplicity that belies its cosmic significance. For any object, you can calculate this critical distance using a beautifully straightforward formula. Take the object's mass, multiply it by twice the gravitational constant and twice the speed of light squared, then divide the whole thing by the speed of light squared. The result tells you exactly how small that object would need to be compressed to become a black hole. For our Sun, this calculation yields a Schwarzschild radius of about 3 kilometers. This means that if we could somehow compress our entire Sun, all of its million-kilometer diameter, all of its nuclear fires and plasma storms, down to a sphere just 6 kilometers across, it would collapse into a black hole. The number seems almost absurdly small when compared to the Sun's actual size, and yet it represents a fundamental threshold in the universe. What makes this radius so special isn't just that it marks where the event horizon forms. It represents the distance at which the escape velocity from an object equals the speed of light. Think about what this means for a moment. We're familiar with escape velocity from our everyday experience, even if we don't usually think about it in those terms. When you throw a ball upward, it slows down as it rises, eventually stops, and then falls back down. But if you could throw it fast enough, about 11 kilometers per second from Earth's surface, it would have enough energy to escape Earth's gravity entirely. The Schwarzschild radius marks the boundary where this escape velocity reaches the ultimate speed limit of the universe. At this distance from a black hole's center, even light, traveling at the fastest possible speed, cannot generate enough velocity to escape. It's not that the black hole grabs light and pulls it back, rather, the geometry of space-time itself becomes so curved that there simply is no outward direction for light to travel. This geometric interpretation of the event horizon reveals something profound about the nature of black holes. They don't violate the speed of light. Instead, they create a region of space-time where the very concept of outward loses its meaning. Inside the Schwarzschild radius, all paths through space-time lead toward the center. This isn't because of some mysterious force, but because the black hole's mass has curved space-time so severely that the geometry itself guides everything inward. To visualize this, imagine a stretched rubber sheet with a bowling ball placed in the center, creating a deep depression. Now picture trying to roll marbles away from the bowling ball while standing inside that depression. No matter which direction you aim, the curved surface of the sheet guides the marbles back toward the center. The Schwarzschild radius represents the edge of a region where this analogy becomes literally true. All directions lead inward. The mathematics of the Schwarzschild solution also reveals something beautiful about the relationship between mass and space. The radius grows linearly with mass, double the mass, and you double the Schwarzschild radius. This means that more massive black holes are less dense at their event horizons. A supermassive black hole with the mass of a billion suns would have an event horizon billions of times larger than a stellar mass black hole, but the average density within that horizon would be much lower. In fact, the largest supermassive black holes have average densities within their event horizons that are less than water. This seems paradoxical. How can something less dense than water trap light itself? The answer lies in understanding that it's not density that creates the gravitational effect, but the total mass and how it curves spacetime. A supermassive black hole creates its inescapable region not through extreme density, but through the cumulative effect of enormous mass acting across vast distances. This relationship between mass and the Schwarzschild radius also tells us something about the formation of black holes. When a massive star collapses, it must compress all of its matter within its own Schwarzschild radius to become a black hole. For most stars, this represents a compression so extreme that matter itself breaks down into forms we can barely imagine. But for the most massive objects in the universe, this compression might not be as severe as we often picture. As we contemplate these geometric relationships, it's worth reflecting on how they connect to our earlier discussions of time dilation. The Schwarzschild radius represents not just a spatial boundary, but a temporal one as well. It marks the distance from a black hole where time dilation becomes infinite from the perspective of a distant observer. Inside this radius, the normal relationship between space and time breaks down so completely that our usual concepts of causality cease to apply. The elegance of Schwarzschild's solution, derived in the trenches of World War I, continues to guide our understanding of the universe's most extreme objects more than a century later. His mathematical insight that space-time curves in response to mass gave us the tools to understand not just black holes, but the expansion of the universe, the bending of light around massive objects, and the gravitational waves that ripple through space when black holes collide. As we journey deeper into the gravitational well of our black hole, we encounter one of the most ethereal and beautiful phenomena in all of physics, the photon sphere. This invisible boundary, located at precisely 1.5 times the Schwarzschild radius, represents a place where the fabric of space-time is curved just enough to allow light itself to orbit the black hole indefinitely. Imagine, if you will, a particle of light, a photon travelling at its eternal strong speed of 300 million meters per second. In the flat space-time far from any massive object, this photon would travel in a perfectly straight line forever, undeviating and constant. But as it approaches our black hole, the curved space-time begins to bend its path, like a marble rolling across a gently warped surface. At most distances from the black hole, this bending simply deflects the photon's path slightly. Light coming from distant stars appears shifted from its true position when viewed past a black hole, creating beautiful gravitational lensing effects that allow us to see multiple images of the same distant galaxy. But at exactly 1.5 times the Schwarzschild radius, something magical happens. The curvature of space-time matches perfectly with the photon's natural tendency to travel in straight lines. At this precise distance, a photon travelling tangentially to the black hole will find its straight-line path through curved space-time forms a perfect circle. The photon enters a stable orbit circling the black hole endlessly at the speed of light. It's as if space-time itself has created a cosmic racetrack for light, where photons can run laps around the black hole for eternity. The photon sphere represents one of the most unstable equilibria in the universe. While photons can orbit there indefinitely in principle, any tiny perturbation will send them either spiraling inward toward the event horizon or escaping outward to infinity. It's like balancing a pencil on its point, theoretically possible but practically impossible to maintain for any real duration. This instability gives the photon sphere a haunting quality. Light that happens to enter this region at just the right angle, and speed will orbit a few times before either being captured by the black hole or escaping to space. From a distance, this creates a strange optical effect, the dim ring of light surrounding the black hole, fed by photons that are spiraling either inward or outward from their brief dance at the photon sphere. The mathematics describing the photon sphere flows naturally from the same equations that describe planetary orbits, but with a crucial difference. Planets orbit in ellipses, following stable paths that can persist for billions of years. But photons, having no mass, cannot follow such stable orbits except at this one critical distance, closer to the black hole, and space-time is too curved for even light speed to maintain an orbit. Farther away, and the curvature is too gentle to trap light in a circular path. What makes the photon sphere particularly fascinating is what it tells us about the nature of light itself. We often think of light as something ethereal, weightless, immune to gravity's pull. And indeed, photons have no mass in the conventional sense, but they do carry energy. And Einstein's insights taught us that energy and mass are equivalent in their gravitational effects. The photon sphere shows us this equivalence in action, so there's some massless particles of light responding to gravity not through weight, but through the curvature of space-time itself. If we could somehow position ourselves at the photon sphere, ignoring for the moment the intense tidal forces that would tear us apart, we would witness one of the most extraordinary views possible in the universe. Looking outward, we would see the rest of the cosmos compressed into a brilliant ring above us, light from all directions focused and concentrated by the black hole's gravitational lensing. But perhaps even more remarkably, looking in the tangential direction, neither toward nor away from the black hole, we might catch glimpses of our own back. Light from our position could travel completely around the black hole and return to us, creating a series of increasingly dim and distorted images of ourselves stretching into the distance. Each image would represent light that had completed one more orbit of the black hole before reaching our eyes. The photon sphere also plays a crucial role in how black holes appear to distant observers. Much of the dramatic visual effects we see in simulations of black holes, the bright accretion disks, the way light seems to bend and twist around the event horizon, result from light's complex behavior near the photon sphere. Photons from the accretion disk can orbit the black hole multiple times before escaping, creating secondary images and caustics that give black holes their characteristic visual signature. This region also helps us understand why black holes appear to have a shadow when observed by telescopes like the Event Horizon Telescope. The shadow isn't the event horizon itself, which is invisible by definition, but rather the photon sphere and the region just inside it. Light from this region is either trapped forever or so severely redshifted that it becomes undetectable, creating the dark silhouette against the bright accretion disk that we observe. The discovery and understanding of the photon sphere represents one of the beautiful intersections between theoretical physics and observational astronomy. What began as a mathematical curiosity in Einstein's equations has become a crucial tool for understanding how we can actually observe and study these cosmic giants. It reminds us that even the most abstract mathematical concepts often find concrete expression in the physical world. As we contemplate the photon sphere, we're witnessing one of gravity's most delicate touches. Not the overwhelming force that creates tidal destruction or the absolute barrier of the event horizon, but a gentle, precise curvature of space-time that creates a sanctuary for light itself. In a universe where everything is in motion, where every orbit eventually decays, where entropy increases and order dissolves, the photon sphere represents a kind of temporal perfection, a place where light can dance forever in the curved space-time around a black hole. As we continue our gentle exploration of what happens to time near a black hole, we find ourselves drawn into an even more fascinating realm of cosmic diversity. You see, not all black holes are created equal, and each type tells its own unique story about time, space, and the very nature of our universe. Like snowflakes falling through an infinite winter sky, each black hole carries its own distinct personality, its own way of bending time and space around itself. Let's begin our journey by imagining the smallest of these cosmic monsters, the stellar mass black holes. These are the ones born from the dramatic death throes of massive stars, typically ranging from about 3 to 20 times the mass of our Sun. Picture, if you will, a star that has lived its entire brilliant life, fusing hydrogen into helium, helium into carbon, and so on up the periodic table, until finally it reaches iron. Iron, you see, is the cosmic dead end. It takes more energy to fuse iron than the process releases, and so the star's nuclear furnace suddenly goes cold. In that moment of stellar death, gravity wins its ultimate victory. The core collapses so rapidly that protons and electrons are crushed together to form neutrons, and if the core is massive enough, not even neutron degeneracy pressure can halt the collapse. The result is a stellar mass black hole, and around these relatively small giants, time behaves in ways that would seem utterly alien to our earthly experience. Imagine approaching one of these stellar mass black holes in your peaceful spacecraft. As you draw closer, you notice something remarkable happening to time itself. The closer you get to the event horizon, that invisible boundary from which nothing can escape, the more dramatically time begins to slow down relative to the outside universe. If you were to hover just outside the event horizon of a 10 solar mass black hole, every second that passes for you would correspond to minutes, hours, or even days passing for observers far away from the black hole's influence. This time dilation becomes so extreme that if you were to wave goodbye to a friend who remained at a safe distance, they would see your wave happening in increasingly slow motion. From their perspective, you would appear to be moving through thick honey, your every gesture becoming more and more languorous until you seemed almost frozen in time. Meanwhile, from your perspective, you would see the entire universe around you speeding up. Stars would be born, live their lives, and die in what seemed like moments to you. But stellar mass black holes are just the beginning of our cosmic story. As we allow our imagination to soar through the vast expanses of space, we encounter black holes of truly staggering proportions, the supermassive black holes that lurk at the hearts of galaxies. These titans can contain the mass of millions, or even billions, of suns, and around them the fabric of space-time is warped in ways that challenge our very understanding of reality. Our own galaxy, the Milky Way, harbours such a monster at its centre. Known as Sagittarius A, pronounced Sagittarius A star, this supermassive black hole contains about 4 million times the mass of our Sun. It sits there in the galactic centre, a silent gravitational anchor around which hundreds of billions of stars dance their eternal waltz. When we observe the stars closest to Sagittarius A, we can actually see the effects of time dilation in action, watching as these stellar dancers slow down and speed up as they follow their elliptical orbits around the invisible giant. The time dilation effects around supermassive black holes are both more gradual and more profound than those around their smaller cousins. Because the event horizon of a supermassive black hole is much larger, potentially larger than our entire solar system, the gravitational gradient is gentler. This means you could actually cross the event horizon of a supermassive black hole without being immediately torn apart by tidal forces, though once inside, your fate would be just as sealed as with any black hole. As you approach the event horizon of such a supermassive black hole, time would still slow down dramatically, but the experience would be less violent, more surreal. You might have hours or even days to contemplate your situation as you drift across that invisible boundary, watching the universe outside speed up around you, seeing the cosmic dance of galaxies accelerate as eons pass in what feels like minutes to you. Then there are the intermediate mass black holes, those mysterious objects that bridge the gap between stellar mass and supermassive black holes. These elusive giants, containing hundreds to thousands of solar masses, have long been theoretical curiosities, but in recent years, astronomers have begun to find evidence of their existence. They represent a fascinating middle ground where time dilation effects are significant but not as extreme as those found near supermassive black holes. Each type of black hole creates its own unique signature in the fabric of space-time, its own particular way of distorting the flow of time. But perhaps the most exotic members of the black hole family are the rotating ones, the Kerr black holes, named after the mathematician Roy Kerr, who first described their properties. When a black hole spins, it literally drags space-time around with it, creating a phenomenon called frame dragging that adds another layer of complexity to our understanding of time near these cosmic giants. In the serene vastness of space, most black holes are not static, motionless objects. Instead, they spin with incredible speed, rotating like cosmic top, and this rotation fundamentally changes how time behaves in their vicinity. These spinning black holes, known as Kerr black holes after the New Zealand mathematician Roy Kerr, who first solved Einstein's equations for rotating massive objects, create some of the most exotic and beautiful distortions of space-time that nature has to offer. Imagine, if you will, a figure skater pulling in her arms during a spin. As her arms come closer to her body, she spins faster and faster, demonstrating the conservation of angular momentum. In a similar way, when a massive star collapses to form a black hole, any rotation it possessed becomes concentrated into a much smaller volume, causing the resulting black hole to spin at tremendous speeds. Some black holes rotate so fast that their event horizons are spinning at nearly the speed of light. This spinning motion creates what physicists call the ergosphere, a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. It's as if the black hole is a giant whirlpool in the fabric of reality, and anything that enters this region is forced to rotate along with the spinning space-time, no matter how hard it might try to remain stationary. The time dilation effects in the ergosphere are particularly fascinating. Not only does time slow down due to the intense gravitational field, but the rotation of space-time itself creates additional complications. From the perspective of a distant observer, objects in the ergosphere appear to be moving in strange, twisted paths. Their motion, a complex dance between the gravitational pull of the black hole and the dragging effect of rotating space-time. Picture yourself approaching a rapidly spinning black hole in your imaginary spacecraft. As you draw near, you begin to feel the effects of frame dragging. Your ship starts to be pulled along with the rotation of the space-time itself. You fire your engines to try to maintain your position, but you find that it becomes increasingly difficult to resist this cosmic current. The very fabric of space and time around you is flowing like a river, and you are being swept along with it. From your perspective inside this swirling maelstrom of curved space-time, time continues to flow normally for you. Your watch ticks at its usual pace, your thoughts unfold at their customary speed. But to an observer far away from the black hole, watching your journey through powerful telescopes, you appear to be caught in a slow-motion ballet, your movements becoming more and more languid as you spiral deeper into the gravitational well. The mathematics of rotating black holes reveals some truly mind-bending possibilities. In the ergosphere, there exist closed time-like curves, paths through space-time that loop back on themselves temporally. This means that in principle, it might be possible to travel into your own past, though the practical difficulties and paradoxes involved make this more of a fascinating theoretical curiosity than a viable time travel method. The fastest spinning black holes create the most dramatic frame dragging effects. These cosmic dynamos can rotate up to 998 times per second, nearly the theoretical maximum before the centrifugal force would overcome gravity and tear the black hole apart. At such extreme rotation rates, the ergosphere becomes a significant feature, extending well beyond the event horizon and creating a complex landscape of curved space-time, where the normal rules of cause and effect become beautifully twisted. As we contemplate these spinning giants, we begin to see how the simple question, what happens to time near a black hole, opens up into a vast tapestry of interconnected phenomena. The rotation of a black hole affects not just the flow of time, but the very nature of space itself. It creates magnetic fields, accelerates particles to incredible speeds, and powers some of the most energetic phenomena in the universe. The jets of material that stream away from the poles of many black holes at nearly the speed of light. These jets are themselves testimony to the strange behavior of time and space near rotating black holes. Material falling towards the black hole gets caught up in the twisted magnetic field lines that thread through the ergosphere. Some of this material is accelerated to tremendous speeds and shot out along the rotation axis of the black hole, creating beams of plasma that can extend for thousands of light years across the cosmos. From the perspective of particles in these jets, time passes normally. But from our distant vantage point, watching these cosmic fountains erupt from the hearts of galaxies, we are seeing the effects of extreme time dilation in action. The particles in these jets are moving so fast and originating from regions where space-time is so severely curved that their entire existence unfolds in a temporal landscape utterly foreign to our everyday experience. In our gentle journey through the mysteries of what happens to time near a black hole, we now encounter perhaps the most spectacular and revelatory events in the entire cosmos, the collision and merger of black holes. These cosmic catastrophes, played out over millions of years but culminating in mere seconds of the most violent activity the universe has ever known, have opened an entirely new window into understanding how time behaves under the most extreme conditions imaginable. Until recently, these cosmic collisions existed only in the theoretical realm, predicted by Einstein's equations but never directly observed. Then, in September 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the gravitational waves produced by two black holes spiraling into each other and merging. This detection didn't just confirm Einstein's century-old predictions, it gave us our first direct glimpse into how time itself behaves during these ultimate cosmic events. Imagine two black holes, each perhaps 30 times the mass of our Sun, orbiting each other in the depths of space. For millions of years, they have been slowly drawing closer together, their orbital dance gradually tightening as energy is carried away by gravitational waves, ripples in the fabric of space-time itself. These waves are incredibly weak, stretching and compressing space by less than 1/10,000th the width of a proton, but they carry within them the story of time's behavior during the most extreme events in the universe. As these two black holes spiral toward their final embrace, something remarkable happens to time in their vicinity. The intense gravitational fields of both objects combine and interfere with each other, creating a complex landscape of curved space-time where time flows at different rates depending on exactly where you happen to be. Near one black hole, time might be flowing at one rate, while near the other it flows at a different rate entirely. In the region between them, time dilation effects ebb and flow like cosmic tides. For hypothetical observers at different locations around this cosmic waltz, the merger would appear to unfold at different speeds. Someone far away from both black holes would see the entire process, the millions of years of gradual inspiral, followed by the final few seconds of rapid merger, playing out at one rate. But observers closer to the action would experience time dilation effects that would dramatically alter their perception of events. An observer positioned near one of the black holes would see their local time flowing normally, but would perceive the rest of the universe, including the other black hole, behaving strangely. The orbital motion might appear to speed up or slow down depending on their exact position and the relative motion of the space-time around them. It's like watching a cosmic dance performance where different parts of the stage are playing at different speeds, creating a surreal ballet of distorted motion and time. In the final moments before merger, when the two event horizons touch and begin to merge into a single, larger event horizon, the behavior of time becomes almost impossible to describe in everyday language. The mathematical models that physicists use to understand these events require supercomputers running for months to solve Einstein's equations in this extreme regime. What they reveal is a space-time geometry so twisted and dynamic that time itself becomes a fluid, ever-changing entity. During the brief instant of merger, lasting perhaps a few hundredths of a second, the two black holes become one, but not without a tremendous release of energy. In that fleeting moment, the merger releases more energy in gravitational waves than all the stars in the observable universe emit in light. This energy comes from the conversion of some of the black hole's mass into pure gravitational radiation, following Einstein's famous equation E = mc2. The newly formed black hole that emerges from this cosmic collision is initially highly distorted, ringing like a struck bell with gravitational waves. These ring-down waves carry information about the final black hole's mass, spin, and other properties. But they also tell us something profound about time itself in the aftermath of such an extreme event. As the newly merged black hole settles into its final configuration, the chaotic space-time geometry gradually smooths out, and the extreme time dilation effects begin to stabilize into the more predictable pattern we would expect around a single massive black hole. It's like watching a pond settle after a stone has been thrown into it, with the ripples gradually fading until the surface becomes calm once again. The gravitational waves that LIGO and other detectors have observed from these mergers are like cosmic messengers, carrying information about events that happened billions of years ago and billions of light years away. When we detect these waves on Earth, we're literally experiencing the effects of extreme time dilation that occurred in the distant past. The waves that stretch and compress our detectors are the same waves that were produced in regions where time was flowing at dramatically different rates compared to our earthly reference frame. Each gravitational wave detection tells us a story not just about the black holes that produced it, but about the nature of time itself under extreme conditions. The frequency and amplitude of these waves encode information about how quickly or slowly events unfolded from different perspectives, giving us unprecedented insight into the relativistic nature of time during the most violent events in cosmic history. As our peaceful exploration of what happens to time near a black hole deepens, we find ourselves at the threshold of one of physics' most beautiful and mysterious realms, the intersection of quantum mechanics and general relativity. Here, at the very edge of black holes, time doesn't just slow down or speed up. It begins to dance with the quantum world in ways that challenge our most fundamental assumptions about the nature of reality itself. In the 1970s, a brilliant young physicist named Stephen Hawking made a discovery that forever changed our understanding of black holes and time. He found that black holes, these seemingly perfect absorbers of everything, including light, actually emit radiation. This Hawking radiation, as it came to be known, emerges from the quantum vacuum right at the event horizon, where the extreme curvature of space-time meets the strange world of quantum uncertainty. To understand this phenomenon, we need to journey into the quantum realm that exists all around us, even in what we call empty space. You see, what we think of as empty vacuum is actually alive with quantum activity. Virtual particle pairs, matter and antimatter twins, are constantly popping into existence and annihilating each other in tiny fractions of a second. Normally, these quantum fluctuations happen so quickly that they have no observable effect on the macroscopic world around us. But near a black hole's event horizon, something remarkable happens to these quantum pairs. The intense gravitational field can separate the virtual particles before they have a chance to annihilate each other. One particle falls into the black hole while its partner escapes into space, becoming real radiation in the process. This is Hawking radiation, and it represents one of the most elegant examples of how quantum mechanics and general relativity work together to create phenomena that neither theory could predict alone. The relationship between Hawking radiation and time is particularly fascinating. From the perspective of a distant observer, this radiation appears to be emitted very slowly from the black hole. The time dilation effects near the event horizon mean that what appears to be a steady, gentle glow of radiation to someone far away corresponds to incredibly rapid quantum processes happening right at the black hole's boundary. Imagine yourself as a patient observer watching a black hole from a safe distance over the course of billions of years. You would see it slowly shrinking as it emits Hawking radiation, gradually losing mass and energy to this quantum process. But here's where the story becomes truly mind-bending. The smaller the black hole becomes, the faster it evaporates, and the more rapidly time appears to flow in its vicinity from your distant perspective. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely through Hawking radiation. But as it loses mass, its event horizon shrinks. The curvature of space-time around it becomes even more extreme, and the time dilation effects become more pronounced. In the final moments of a black hole's life, when it has shrunk to the size of an elementary particle, it would appear to an outside observer to suddenly explode in a brief flash of energy, releasing all of its remaining mass in an instant. But here's the truly remarkable part. From the perspective of someone falling into the black hole, none of this would be apparent. The person crossing the event horizon would see nothing unusual about Hawking radiation or the black hole's evaporation. Time would continue to flow normally for them, and they would pass through the event horizon as if it were just another region of space, blissfully unaware that to the outside universe, the image would be frozen at the horizon, slowly red-shifting and fading away as the black hole itself evaporates around them. This creates one of the most profound puzzles in modern physics, the black hole information paradox. When matter falls into a black hole, it carries information about its quantum state, its history, its properties. But when the black hole evaporates through Hawking radiation, where does that information go? Quantum mechanics tells us that information cannot be destroyed, but general relativity suggests that anything crossing the event horizon is lost forever. Recent theoretical work suggests that the resolution to this paradox may lie in the quantum nature of space-time itself. Some physicists propose that the event horizon is not a smooth boundary, but rather a quantum mechanical surface where information is encoded in incredibly subtle correlations between the outgoing Hawking radiation and the black hole's interior. This would mean that time near a black hole is not just curved by gravity, but also quantized, broken up into discrete quantum chunks at the smallest scales. The implications for time itself are staggering. If space-time is indeed quantized near black holes, then our continuous notion of time, flowing smoothly from past to future, may be just an approximation that breaks down under extreme conditions. Time itself might be made up of discrete units, quantum moments that are the temporal equivalent of atoms, indivisible and fundamental. As we contemplate these quantum whispers at the edge of forever, we begin to see that the question, what happens to time near a black hole, opens up not just into the realm of curved space-time and gravitational physics, but into the very foundations of reality itself. The intersection of quantum mechanics and general relativity near black holes suggests that time, space, matter, and information are all deeply connected in ways we are only beginning to understand. As we continue our gentle journey into the mysteries of what happens to time near a black hole, we encounter perhaps the most mind-bending concept in modern theoretical physics, the holographic principle. This remarkable idea suggests that all the information contained within a black hole, including information about how time flows inside it, might actually be encoded on its two-dimensional surface, the event horizon itself. To understand this concept, imagine a hologram, one of those shimmering images that appears three-dimensional but is actually stored on a flat, two-dimensional surface. When you look at a hologram from different angles, you see different perspectives of the three-dimensional image, even though all the information is actually contained in the flat surface. The holographic principle suggests that black holes work in a similar way. All the three-dimensional physics happening inside the black hole, including the complex behavior of time in its interior, might be perfectly described by information stored on the event horizon. This idea emerged from the work of physicists trying to understand black hole thermodynamics, the study of how black holes behave like giant thermodynamic systems. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have temperature and entropy, just like any other thermodynamic system. But they found something surprising. The entropy of a black hole is proportional not to its volume, as you might expect, but to the area of its event horizon. This was revolutionary because entropy, in thermodynamics, measures the amount of information contained in a system. If a black hole's entropy depends on the area of its horizon rather than its volume, this suggests that all the information about the black hole's interior, including how time flows within it, is somehow encoded on the horizon's surface. From the perspective of someone far away from the black hole, watching matter fall toward the event horizon, this holographic picture makes a kind of sense. As we've discussed, time dilation causes infalling matter to appear to slow down and freeze at the horizon, never quite crossing it from the outside observer's perspective. In the holographic view, this frozen information on the horizon contains a complete description of everything that has ever fallen into the black hole, including a record of how time was flowing for each piece of infalling matter. But here's where the story becomes truly extraordinary. Recent developments in theoretical physics suggest that this holographic principle might not be limited to black holes. Some physicists now believe that our entire universe might be holographic, that all the three-dimensional physics we observe, including the complex ways that time flows in different gravitational fields, might actually be encoded on a distant two-dimensional boundary. This holographic universe idea, known as the ADS-CFT correspondence, suggests a deep duality between gravity and the bulk of space, including black holes and their time dilation effects, and quantum field theory on the boundary. It's as if our three-dimensional universe, with its curved space-time and complex temporal relationships, is actually a holographic projection from a simpler two-dimensional reality. In this holographic view, time near a black hole takes on an almost mystical quality. The time dilation effects that we observe, the slowing of clocks, the stretching of moments into eternities, might be manifestations of how information flows and is processed on the holographic boundary. Time itself becomes a kind of emergent phenomenon, arising from the complex interactions of information encoded on a distant surface. Consider what this means for our understanding of what happens to time near a black hole. If the holographic principle is correct, then the extreme time dilation near a black hole's event horizon isn't just a gravitational effect. It's a reflection of how information about the black hole's interior is encoded and processed on the horizon. Every clock that slows down near a black hole, every process that appears to freeze from a distant observer's perspective, is part of a vast computational process happening on the horizon's holographic surface. This perspective offers new insights into some of the paradoxes we've discussed. The black hole information paradox, the question of what happens to information that falls into a black hole, might be resolved if that information never actually crosses the horizon, but instead becomes encoded on its surface. From the holographic perspective, nothing ever truly falls into a black hole. Instead, it becomes part of the complex holographic pattern on the event horizon. The implications for time itself are profound. If time near black holes is indeed holographic, if temporal relationships are encoded on distant boundaries rather than existing independently in the bulk of space, then our entire understanding of causality and temporal order might need to be reconsidered. Past, present, and future might not be absolute concepts, but rather emergent properties of how information is organized and processed in the holographic description of reality. As we contemplate these ideas floating peacefully through our cosmic meditation on black holes and time, we begin to see that the simple question we started with has led us to the very frontiers of human knowledge. The behavior of time near black holes isn't just about curved space-time and gravitational physics. It's about the fundamental nature of information, reality, and existence itself. In the holographic universe, every moment you experience, every tick of your clock, every memory you form might be part of a vast holographic computation happening on the boundary of space and time. The time dilation effects near black holes become windows into this deeper reality, showing us how time emerges from the processing of information in ways we are only beginning to understand. This holographic perspective also suggests that black holes might be the universe's ultimate computers, processing information about space-time and temporal relationships in ways that far exceed any technology we could ever build. The event horizon becomes not just a boundary between inside and outside, but a vast computational surface where the universe stores and processes information about the nature of time itself. As we continue our gentle exploration of what happens to time near a black hole, we find ourselves at a beautiful crossroads where science becomes poetry, where mathematics transforms into music. The gravitational waves that ripple through space-time when black holes collide create what scientists lovingly call the symphony of the universe. These waves, predicted by Einstein over a century ago, were only detected in 2015, and they've opened an entirely new window into understanding how time itself behaves in the most extreme environments imaginable. Picture, if you will, two black holes dancing together in the cosmic darkness. They've been orbiting each other for millions of years, gradually spiraling closer and closer together. As they dance this ancient waltz, they create ripples in the very fabric of space-time itself. These ripples travel outward at the speed of light, carrying with them the story of time's behavior in the most intense gravitational fields in the universe. When these waves finally reach Earth, they stretch and compress space by distances smaller than a proton, yet our incredibly sensitive instruments can detect these whispers from the cosmos. What's truly remarkable about these gravitational waves is that they carry information about time itself. When two black holes merge, the final moments of their dance happen incredibly quickly from our perspective. But if you could somehow observe this event from close by, time would behave in the most extraordinary ways. The closer you were to this cosmic collision, the more dramatically time would slow down for you relative to observers far away. In the final milliseconds before the black holes merge, time near the event would be stretched and warped in ways that challenge our everyday understanding of reality. The gravitational waves themselves are like fossils of distorted time, carrying the signature of how space-time was curved and twisted during these cataclysmic events. When scientists analyze these waves, they're not just studying distant collisions, they're studying the very nature of time itself. Each wave contains information about how gravity affects the flow of time, providing us with experimental evidence for concepts that were once purely theoretical. It's as if the universe is sending us postcards from the most extreme environments possible, telling us stories about what happens to time when gravity becomes overwhelming. These discoveries have given us a new appreciation for Einstein's vision of space-time as a dynamic, flexible medium rather than a rigid stage on which events unfold. Time isn't just something that passes uniformly everywhere in the universe. It's intimately connected to the matter and energy around it. Near black holes, this connection becomes so extreme that time essentially becomes another dimension of space, warped and twisted by the immense gravitational fields. The gravitational waves we detect are the ripples from this cosmic dance, carrying the echo of time's strange behavior in these extreme environments. As we listen to these cosmic symphonies, we're reminded that our understanding of time near black holes isn't just an abstract scientific curiosity. These discoveries help us understand the fundamental nature of reality itself. They tell us that time is not the constant, unchanging flow we experience in our daily lives, but rather a flexible dimension that responds to the presence of matter and energy. This knowledge has profound implications for our understanding of the universe, from the behavior of the smallest particles to the evolution of the cosmos as a whole. One of the most mind-bending discoveries in our journey to understand what happens to time near a black hole has led scientists to propose something called the holographic principle. This idea suggests that all the information contained within a volume of space can be encoded on its boundary, much like how a hologram stores three-dimensional information on a two-dimensional surface. When applied to black holes, this principle has revolutionary implications for our understanding of how time behaves near these cosmic giants. Imagine for a moment that you're looking at a black hole from a safe distance. According to the holographic principle, all the information about what's happening inside the black hole, including information about time itself, might be encoded on the event horizon. This means that the three-dimensional reality we perceive might actually be a projection from information stored on a two-dimensional surface. It's like discovering that what we thought was a sculpture is actually a shadow cast by something far more complex and beautiful. This cosmic perspective helps us appreciate that our study of black holes and time isn't just an intellectual exercise, but a way of understanding our own origins and place in the universe. When we observe the behavior of time near these gravitational giants, we're studying the aftermath of the same stellar processes that created the elements that make up our planet and our bodies. The extreme curvature of space-time near black holes tells the story of stellar death and rebirth that has been playing out across the cosmos for billions of years. The supermassive black hole at the center of our galaxy has been influencing the evolution of the Milky Way throughout its entire history. The gravitational effects of this ancient giant have helped shape the spiral structure of our galaxy, influenced the formation of new stars, and indirectly affected the conditions that allowed our solar system to form in a stable region of space. In a sense, the time dilation effects we observe near this black hole are part of the same cosmic story that led to our existence as conscious beings capable of contemplating the nature of time itself. Our cosmic heritage also includes the gravitational waves that ripple through space-time when black holes merge. These waves carry information about events that happened billions of years ago, when the universe was young and very different from today. When we detect these waves, we're receiving messages from the deep past, learning about cosmic events that help shape the large-scale structure of the universe we inhabit today. The time dilation effects encoded in these gravitational waves tell us about the conditions that existed when the first galaxies were forming, and the first supermassive black holes were growing to maturity. This connection to our cosmic heritage also reminds us that we are not separate from the universe we study, but are instead integral parts of the cosmic story that has been unfolding for nearly 14 billion years. The same physical laws that govern the behavior of time near black holes also govern the chemical processes in our cells, the electrical activity in our brains, and the gravitational forces that keep us anchored to our planet. We are not outside observers of cosmic phenomena, but rather conscious expressions of the universe's capacity for self-awareness and understanding. The realization that we are made of ancient starlight shaped by cosmic processes that include the formation and evolution of black holes adds a profound dimension to our exploration of time in these extreme environments. When we study what happens to time near a black hole, we're not just satisfying scientific curiosity, but are engaging in a form of cosmic self-discovery, learning about the fundamental processes that made our existence possible and continue to shape our cosmic environment. Our journey through the mysteries of what happens to time near a black hole has been a dance between theory and observation, between mathematical prediction and experimental verification. This dance of discovery has been one of the most beautiful aspects of black hole physics, showing us how human creativity and cosmic reality can come together in moments of profound understanding and wonder. The story began over a century ago with Einstein's revolutionary insight that space and time are not separate entities, but form a unified space-time that can be curved by the presence of matter and energy. This purely theoretical breakthrough predicted the existence of objects so massive that they curve space-time to the point where not even light could escape. For decades, these black holes remained mathematical curiosities, existing only in the equations and imaginations of theoretical physicists. The dance between theory and observation began in earnest when astronomers started finding evidence for these theoretical objects in the real universe. The discovery of Cygnus X1, the first widely accepted black hole candidate, marked a pivotal moment when mathematical prediction met observational reality. Suddenly, the abstract concepts of curved spacetime and time dilation became concrete features of objects we could actually study in the cosmos. The time dilation effects that had been predicted by Einstein's equations were no longer just theoretical possibilities but measurable phenomena occurring in real celestial objects. This dance has accelerated dramatically in recent years with the development of increasingly sophisticated observational techniques. The detection of gravitational waves by LIGO and Virgo has allowed us to observe black hole mergers directly, providing unprecedented insight into how time behaves during the most extreme gravitational events in the universe. These observations have confirmed theoretical predictions with remarkable precision, while also revealing new phenomena that theorists hadn't fully anticipated. The recent images of black holes captured by the Event Horizon Telescope represent another beautiful moment in this ongoing dance of discovery. These images show us the shadow of the event horizon itself, the boundary where time dilation becomes so extreme that light cannot escape. What we see in these images is not just the black hole itself, but the distorted space-time around it, including regions where time flows at different rates depending on distance from the gravitational source. The dance continues with each new theoretical insight and observational breakthrough. Quantum theories of gravity are making new predictions about what happens to time at the very center of black holes, while advanced computer simulations are showing us how space-time itself behaves during black hole mergers. Future space-based gravitational wave detectors will extend our observational reach, allowing us to study black holes and time dilation effects throughout the observable universe. This ongoing dance between theory and observation is particularly beautiful because it shows us how science progresses through the interplay of imagination and empirical testing. The most profound insights about the nature of time near black holes have come from creative theoretical work that pushed beyond the boundaries of conventional thinking, followed by ingenious observational techniques that found ways to test these bold predictions against reality. Each cycle of this dance has deepened our understanding while revealing new mysteries to explore. The collaborative nature of this scientific dance is also worth celebrating. The discoveries we have explored together represent the work of countless scientists from around the world, each contributing their unique insights and expertise to our collective understanding of black holes and time. Theorists work alongside observers, experimentalists collaborate with computer modelers, and engineers develop the sophisticated instruments that make new observations possible. This global collaboration shows us how human knowledge advances through the combined efforts of many minds working toward common goals. As we near the end of our peaceful exploration of what happens to time near a black hole, let's take a moment to appreciate the gentle mysteries that continue to surround the nature of time itself. While we've learned an incredible amount about how time behaves in the extreme gravitational environments around black holes, there are still profound questions that remind us how much wonder remains in our understanding of temporal reality. One of the most beautiful mysteries involves the subjective experience of time dilation near black holes. While we can calculate precisely how time slows down for an observer approaching the event horizon, we can only imagine what this experience might actually feel like. Would someone falling into a black hole be aware that their time is slowing relative to the outside universe? Or would time continue to feel normal to them, while the external universe appeared to speed up dramatically? These questions touch on the deep connection between physical time and conscious experience, reminding us that time is not just a mathematical concept, but something we experience directly in our daily lives. The relationship between quantum mechanics and gravity near black holes presents another gentle mystery that continues to fascinate physicists. Quantum theory tells us that empty space is actually filled with virtual particles that constantly appear and disappear, borrowing energy from the vacuum and then returning it in accordance with Heisenberg's uncertainty principle. Near the event horizon of a black hole, these quantum fluctuations interact with the extreme curvature of space-time in ways that we're still learning to understand. This interaction might be responsible for Hawking radiation, but the detailed mechanisms remain beautifully mysterious. The information paradox presents perhaps the most profound mystery in our understanding of black holes and time. If black holes eventually evaporate through Hawking radiation, what happens to the information that fell into them? Quantum mechanics insists that information cannot be destroyed, but general relativity suggests that anything falling past the event horizon is lost forever. This paradox forces us to question our deepest assumptions about the nature of information, time, and reality itself. The resolution of this mystery will likely require a new understanding of how space-time emerges from more fundamental information theoretic processes. There's also the beautiful mystery of what lies beyond the event horizon. Our current theories suggest that space-time becomes increasingly distorted as you approach the singularity at the center of a black hole, with time dilation effects becoming infinite at the center itself. But this mathematical singularity likely signals the breakdown of our current theories rather than the actual behavior of time and space in these extreme conditions. New theories of quantum gravity suggest that the interior of black holes might contain structures and phenomena that we can barely imagine, possibly including connections to other regions of space-time or even other universes entirely. The mystery of time's arrow becomes particularly intriguing when considered in the context of black holes. Why does time seem to flow in only one direction throughout most of the universe? Black holes play a crucial role in this question, because they represent regions where the normal causal structure of space-time breaks down. At the event horizon, the distinction between space and time becomes blurred, and inside the black hole, the roles of space and time coordinates actually interchange. Understanding these extreme conditions might provide clues about the fundamental origin of time's directional flow. Perhaps most mysteriously of all, the study of black holes suggests that time itself might be an emergent property rather than a fundamental aspect of reality. Some theories propose that time arises from more basic information processing operations, similar to how temperature emerges from the microscopic motion of atoms. If this is true, then the extreme time dilation effects we observe near black holes might be revealing something profound about the computational nature of reality itself. This perspective suggests that understanding what happens to time near a black hole might ultimately teach us about the deepest levels of cosmic information processing. These gentle mysteries remind us that science is not about eliminating wonder from the universe, but about discovering ever deeper sources of awe and curiosity. Each answer we find about the behavior of time near black holes reveals new questions that we hadn't even thought to ask before. This endless frontier of discovery keeps science vibrant and ensures that future generations will have their own opportunities to explore the beautiful mysteries of time and space. As we prepare to conclude our gentle exploration of what happens to time near a black hole, it's worth reflecting on the extraordinary journey we've taken together through the cosmos. We began with simple questions about how time behaves in strong gravitational fields, and we've discovered a universe far stranger, more beautiful, and more interconnected than we might have imagined when we started this peaceful voyage of discovery. We've learnt that time is not the constant, unchanging flow we experience in our daily lives, but rather a dynamic aspect of reality that responds to the presence of matter and energy. Near black holes, this responsiveness becomes so extreme that time itself becomes malleable, stretching and compressing in ways that challenge our everyday understanding of temporal flow. This discovery has profound implications not just for our understanding of black holes, but for our comprehension of the fundamental nature of reality itself. Our journey has taken us from the theoretical insights of Einstein's general relativity to the cutting-edge observations of gravitational wave detectors and the Event Horizon Telescope. We've seen how the dance between theory and observation has gradually revealed the secrets of these cosmic giants, showing us that the universe is even more remarkable than our boldest theoretical prediction suggested. The recent detection of gravitational waves and the first images of black hole event horizons represent milestones in human understanding that will be remembered for centuries to come. We've explored how the extreme conditions near black holes serve as natural laboratories for testing our most fundamental theories about space, time, and gravity. These cosmic extremes push physics to its limits, revealing phenomena that we could never study under terrestrial conditions. The time dilation effects we've discussed aren't just exotic curiosities, but windows into the deepest workings of space-time itself. Through studying these effects, we've gained insights into the holographic nature of reality, the information-theoretic foundations of physics, and the possible emergence of time from more fundamental processes. Our exploration has also connected us to our cosmic heritage, reminding us that the same stellar processes that create black holes also forge the elements that make up our bodies and our world. The extreme gravitational environments we've studied are part of the same cosmic story that led to our existence as conscious beings capable of contemplating the nature of time itself. This perspective helps us appreciate that we're not separate from the universe we study, but rather integral parts of its ongoing evolution and self-discovery. We've encountered beautiful mysteries that continue to puzzle the brightest minds in physics, from the information paradox to the nature of singularities. These unsolved problems remind us that science is an ongoing adventure, with each answer leading to new and deeper questions. The mysteries surrounding black holes and time ensure that future generations of scientists and curious minds will have their own opportunities for discovery and wonder. Throughout our journey, we've maintained a sense of gentle wonder and appreciation for the profound beauty of the cosmos. The extreme physics of black holes could easily seem intimidating or incomprehensible, but by approaching these topics with patience and curiosity, we've discovered that even the most exotic phenomena can be understood and appreciated by anyone willing to embark on this journey of discovery. The universe reveals its secrets not just to professional scientists, but to anyone who approaches it with genuine curiosity and an open mind. Our exploration has also highlighted the collaborative nature of scientific discovery. The insights we've shared represent the work of countless scientists from around the world, each contributing their unique perspectives and expertise to our collective understanding. This global collaboration shows us how human knowledge advances through the combined efforts of many minds working toward common goals of understanding and discovery. As we prepare to conclude our journey, it's important to recognize that our exploration of what happens to time near a black hole is really just the beginning of a much larger adventure. The concepts and insights we've discussed provide a foundation for understanding not just black holes, but the broader cosmos in which we live. The study of time dilation and gravitational effects connects to everything from the GPS satellites that help us navigate our world to the fundamental processes that govern the evolution of the universe itself. The time dilation effects we've explored also have practical implications for humanity's future as a spacefaring species. As we expand into the solar system and eventually to the stars, we'll need to account for the effects of gravity on time in environments very different from Earth. The knowledge we've gained from studying black holes will help prepare us for these future adventures, ensuring that we can navigate the cosmos with the same precision and understanding that we navigate our terrestrial world. Most importantly, our journey has reminded us of the profound interconnectedness of all things in the universe. The same physical laws that govern the behavior of time near black holes also govern the chemistry of life, the structure of atoms, and the evolution of stars and galaxies. By understanding these fundamental principles, we gain insight not just into exotic cosmic phenomena, but into the basic processes that make our existence possible. Thank you for staying with me through this peaceful journey into what happens to time near a black hole. Together, we've explored some of the most profound mysteries in the universe, from the nature of time itself to the holographic principle that might govern all of reality. We've seen how black holes serve as cosmic laboratories for testing our deepest theories about space, time, and information, and we've discovered that these exotic objects are intimately connected to our own existence and cosmic heritage. I hope this gentle exploration has sparked your curiosity about the cosmos and inspired you to continue learning about the beautiful mysteries that surround us. The universe is vast and full of wonders waiting to be discovered, and each of us has the opportunity to participate in this ongoing adventure of understanding and discovery. Whether you're drawn to the theoretical physics of black holes, the observational astronomy that reveals their secrets, or simply the philosophical implications of what we've learned about time and space, there are countless paths for further exploration. Remember that science is not just about memorizing facts or understanding equations, but about maintaining a sense of wonder and curiosity about the world around us. The same curiosity that drove Einstein to develop his theories of relativity, that motivated the engineers who built gravitational wave detectors, and that inspires today's theoretical physicists to explore the deepest mysteries of black holes, lives within each of us. By nurturing this curiosity and approaching the universe with patience and openness, we can all participate in the grand human adventure of understanding our place in the cosmos. As you continue your own journey of discovery, I encourage you to remember the gentle mysteries we've explored together. The time dilation, effects near black holes, the holographic principle, the information paradox, and all the other phenomena we've discussed are not just abstract concepts, but windows into the fundamental nature of reality itself. Each time you look up at the night sky, remember that you're seeing a universe where time and space dance together in the most extraordinary ways, where massive black holes warp the very fabric of existence, and where the same physical laws that govern exotic cosmic phenomena also make your own existence possible. The cosmos is calling to all of us, inviting us to explore its mysteries and discover its secrets. Our exploration of what happens to time near a black hole has been just one small part of this grand adventure, but it has shown us how much beauty and wonder await those who are willing to look beyond the familiar and venture into the unknown. The universe is not just our home, but our greatest teacher, constantly revealing new lessons about the nature of reality, time, space, and our place within the grand cosmic story that continues to unfold around us. Thank you once again for joining me on this peaceful journey through the mysteries of time and black holes. May your curiosity continue to grow, may your sense of wonder never fade, and may you always remember that you are made of ancient starlight, participating in the universe's ongoing quest to understand itself. Until we meet again in another exploration of cosmic mysteries, keep looking up, keep wondering, and keep exploring the beautiful universe that surrounds us all.